Okay, so today we're going to be differentiating in polar form. So there were lessons that introduce you to polar coordinates and polar equations. So your polar coordinates get plotted on what's called a polar coordinate system. And it looks a little bit different after this point. So you can actually take the polar coordinate system and superimpose it onto a rectangular coordinate system. But you know the rectangular coordinate plane, x, y, it's a grid and it's made up of squares. But you know, squares are rectangles. That's why we call it a rectangular coordinate plane. But like if let's say we take our polar coordinate plane and put it on top, however is 1 unit around, you're going to have a circle and it has a radius of 1. And the next circle at 2 units away from what we call the origin, okay, that creates a circle and that has a radius of 2. So we have polar equations that could be like something like r equals 2. And the lines that we see here, they're actually our angle measures to plot our points. We find the angle that we're referring to, and we call that theta, and then we refer to r, so we know on what circle that we want to plot that point. So the angle here would be 0. The angle here is pi over 2, because it makes a right angle, and we know that is 90 degrees. Please remember them in radians. This is pi. This is 3 pi over 2, and we come back around. So this is 2 pi, and so on. So if it so happens that you have an r value that's negative, remember r is indicating the radius. So what happens is actually doing a transformation. So if let's say you have the angle of -2, 0, so you go to the angle of 0, and instead of plotting it over here, because that would be where r is a positive 2, you reflect it over through what we call the pole. I'm going to talk about that spot, and it shouldn't really be another circle because then it looks like another radius, and it comes over on this other side. So we don't refer to this place as the origin, we call it the pole, and the pole is where the angle measure is 0 and the radius is 0. Okay, and actually with any radius of 0, you're going to be on the pole. So I can even say like this is the pole, that is the pole. And then you can also have other angle measures within your coordinate, your polar coordinate system. So such as if we go up by 30 degrees or pi over 6, and then we have like pi over 3 over here. This would be 2 pi over 3. This would be 5 pi over 6, and so on. So do be familiar with those angles as you go around what you're known as the unit circle. This would be like your unit circle right here as you go around to label all the angles. And you also have pi over 4. Okay. So that's also a good one, I should say. So we have like pi over 4, and we have 3 pi over 4, 5 pi over 4, 7 pi over 4. So, and you could also know these as like negative angles, like this is negative pi over 4. That could be helpful when you have to write integrals to know them both. So do be familiar with that. It is helpful. And if you need some extra like lessons all the time, just let me know. If I ask for questions, this is where you could kind of like give me a heads up. Now, the other lessons that I have given you for polar coordinates are probably helpful, and I'm just repeating a lot of things that are in it. What we're going to focus on today is doing differentiation. on our polar equations. And in order to do that, we need to understand how to take a derivative when we're working with polar coordinates. So let me pull something else up while I take away this scribble, and hopefully you had some time to write down the example that we're going to do, and I'm going to actually extend on this example. So let's go like example 1. I'm going to do a few other things with it as well. Okay, so we have to first understand that we have these conversions. Hopefully you can see this here. So x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. And r is our polar equation. So that is the function that we're looking at, okay? And it's a function of theta. So we can consider that r can also be replaced with f of theta, as you can kind of see over here. But these are like our main, I want to say, expressions that we have. And so this is what's going to be helpful when we have to take a derivative. Okay, so let's take a look at this example. Let's call this example 1. Okay, so it says to find the slope of the rose curve. So we call this a rose curve if you identify your polar equations. This is the graph where there would be 3 petals, because n times theta, if n is odd, it's just that many petals. And so we call it a rose curve. And so if it's asking for the slope of the curve, it's actually just asking for its derivative. And it says at this particular instant, at the point where theta is equal to pi over 6. Now, a lot of times you can be asked for finding like the instant rate of change, instantaneous rate of change. At theta is equal to pi over 6. So it means the same thing. We need to take the derivative. You can be asked to find the slope of the line that's tangent to the curve that's given, and you look at the curve that's given, and if it's this tangent line or the slope of the tangent line, well, it's the same as finding the slope of the curve. Okay? So all basically the same thing. That you may be asked. You may also be asked to find a second derivative. So if you remember in the beginning of the video, I may do some other things with you, and that can be one of them. So let's go back to, this is an instantaneous rate of change, okay? And sometimes it's also just called rate of change. So when you find the rate of change of a polar curve, you're finding the rate of change, d over d theta, of r, of your radius. So rate of change of your radius r. And that answer is either going to tell you whether you're moving away from or toward the pole. So going back to, we don't call it the origin anymore, it's called the pole. So if they ask you like to find in words, that's what you have to say. The rate of change of radius r away from or toward the pole. Okay, if it's positive or negative. So now you know that we're finding the rate of change of radius r. So that means we have to look at our equation for r and just take the derivative. I'm trying to erase this here so you can see this clearer. With respect to theta. Okay, so derivative with respect to theta is dr over d theta. So we're going to work this out. This is going to be chain rule. So outside times the derivative of the inside, and derivative of the inside is going to be 3. So 3 times 2, and it's going to be cosine of the angle 3 theta. So that comes out to be 6 cosine of 3 theta. So now all we need to do at this point is substitute where theta is equal to pi over 6. So we're going to have 6 times cosine of 3 times pi over 6. 3 can go into 3 once. 3 goes into 6 2 times. So it's a cosine of pi over 2. Cosine of pi over 2 is 0. And 0 times 6 is going to still be 0. Okay, so we end up finding that the slope of the rose curve r equals to sine of 3 theta at the point where theta is pi over 6 is just 0. That's the slope. So, like I said, I'm going to extend upon this a little bit. So we're asked to find the rate of r with respect to theta in this particular example. But what if they had asked to find the rate of change of x with respect to theta? So if we want the rate of change of x with respect to theta, okay, this is where those formulas that we're talking about down here are going to come into play. So x is equal to r times the cosine of theta. So we're going to take that value or expression for r and plug that in to the formula that x is equal to r times the cosine of theta. Okay, so if we want the derivative of x with respect to theta, or rate of change of x with respect to theta, then we have this expression here, and hopefully you see it. It is going to need the product rule. Okay, so first times the derivative of the second. Okay, plus second times the derivative of the first. Okay, and this again we kind of did before, so this is going to be, so it was a glitch with this program and it kind of went away, so I'm going to do it again just real fast as my fingers can go. Alright, so I was up to saying, hey, you know what? We did do the derivative of r before with respect to theta, so all we need to do is make sure we multiply our previous answer with the cosine of theta. And at this point, there's really not a lot of rewrite or simplifying because, I mean, I may put the negative sign in front. You have different angle measures in each of these terms. So there's not much to really do here. Like I pulled out the -1, so I multiplied it with 2. I'm pulling the 6 out in front of this, or you could just reorder it. It doesn't really matter. There's not much simplifying. Now, you could also be asked to find the rate of change of y with respect to theta. Okay? So if that's the case and you need to find the rate of change, okay, of y with respect to theta, then you need dy over d theta. So I'm going to come over here and write y is equal to r sine of theta. Coming back to these equations again. So if r is 2 sine of 3 theta, and we know y is equal to r sine of theta, then we're multiplying these two. So once again, we need product rule. Okay, so don't forget, first derivative of the second plus second derivative of the, this was a 3, by the way, of the first. Okay, so let's keep it as like one long answer here. Don't forget chain rule. There's our answer again. That's a S and in the word cosine, and there's a 3. All right. And that's it. Like I said, you know, if you want, you can rewrite this, like bring the 6 in front, but I'm really not changing much around here. So this is if we're asked to find the rate of change of y with respect to theta. Okay. And that's really it. All right, if you're asked any one of these, then you're finding out how the point is moving away or towards the pole in either the x direction or the y direction. And remember, this is the rate of change of the radius, okay, and how it's going away from or toward the pole, okay? And like I said before, one more thing about like the second derivative. Well, we need the first derivative in order to do the second derivative. And I went through all this below, so let me erase just this little tiny piece up here. I went through all of this so we can find dy over dx, and then we'll talk about the second derivative. So dy over dx is going to be dy over d theta and it's going to be a while trying to write this all out again. Okay. Remember, I'm now bringing this 6 in front, and you don't need the parenthesis there. It's just maybe neater for some students. Okay. So that was the dy over d theta. If I divide it by dx over d theta, then I have dy over dx. So let me take the answer for the dx over d theta. Now, try not to cancel or factor anything here because we have two different terms. Okay, the plus sign means there's two different terms here. So we're not going to be able to cancel anything unless they're factors. You can only cancel factors. So maybe if there was some factor you can pull out, but there really isn't other than maybe a 2 or a negative 2. I would just probably leave it at this point. Okay, so how do we get d squared y over dx squared? Okay, so let me erase a little bit of this. Hold on. Okay, so we found d y over dx by doing dy over d theta divided by dx over d theta, and if you do keep change flip here, the d thetas cancel. Now, I know it didn't ask for the slope of the tangent line, but if you were to plug in pi over 6 into this expression, you're going to get an answer of negative radical 3. Okay? Yes. You got negative radical 3. And if you look at that tangent line, now that makes sense. You got a negative slope there. It turns out to be negative radical 3. So, just to let you know how that answer is a little bit different than before. Before, we got the rate of change of the radius, okay, as we're moving away from or toward the pole, so it's 0 because there wasn't a change. But now we have an answer of the slope of the tangent line. So let's get to that d squared y over dx squared. And we've done these problems before a little bit with like the parametric equations, because if this looks familiar, we did parametric equations, except instead of theta, it was t. So in order to do the second derivative, we need to take the derivative of our dy over dx with respect to x. Okay, so that means that in order to do this particular problem, we need to kind of break up what we're doing, okay, for that dy over dx, okay, and take its derivative with respect to theta, because we can see our answer over here, everything's in terms of theta. So we're going to have d over d theta of our dy over dx. So that dx that was left in the denominator has to be the dx over d theta. Okay? So it's a long way to explain it. So basically you need the answer of dx over d theta once again. Okay? So that's that denominator that we had before, and we have to take the derivative, okay, so I'm just borrowing it, of the whole fraction. So that means you do need to do quotient rule. For a problem like this one, you probably are not going to get, I want to say, a curve like this, because who would want to do the quotient rule for this expression? But I just wanted to let you know as a heads up, just in case it ever showed up on your AP exam. And I want you guys to do well. So that's it. That's everything I could possibly think of that has to do with derivatives and polar equations and polar coordinates. And if you still have questions, let me know. Good luck.